Reaqtor, reliable RX at scale for high-performance event processing. And my goal is for the meaning of that title to be understandable by the end of this talk. So what exactly is Reaqtor and why am I talking about it? So Reaqtor is a system for stateful, reliable, distributed processing of events. And it's based on the programming model that originated from the reactive extensions for .NET. So RX, the reactive extensions for .NET, have been an open source project for a very long time now, also under the .NET Foundation ownership, but more recently, another project that grew out of the same source in Microsoft became open source, and that's also under the ownership of the .NET Foundation. And we at Engine, my employer, we are the main maintainers of this, and we were particularly interested in it because it provides a model for doing high volume, real-time online analytical processing of event-driven sources. I'm going to talk about some of the application types that we have found it to be applicable to, but it's basically really good if you've got event sources that generate data on their own schedule, potentially at very high volumes, and you want to do analytics over it where there might be very large numbers of distinct entities of interest. So that's the broad idea behind it. And to understand how it works and what the nature of Reaqtor is, it's useful to understand a little bit about where it came from and why it was invented. So this actually grew out of a project inside of Microsoft. So this was originally written by Microsoft. It was an internal piece of technology, and we at Engine were helping to try and get it actually open sourced over the course of several years, and it eventually came out in 2021. And it came originally out of the Cloud Programmability group. So the Cloud Programmability group was formed back in the days when Azure was very new, and Microsoft was concerned about how easy it would be for developers to exploit the potential of a cloud-based platform. And so they were looking at potential new programming models that could help developers get to grips with this. And one of the things that they came up with was a project called Volta, which was talked about publicly, but it was never actually released. And some of the ideas in it were a long way ahead of their time, and some of it's now come to light in things like Blazor. But one of the main things that did come out of it was RX, the reactive extensions for .NET. But they were actually originally designed to support cross-layer event communication. So one of the models they had in mind was that you might be building a user interface that would run in the browser. You might have some sort of middle tier running in some servers on Azure in the back end, and then maybe other lower levels behind that. And they wanted to have a reliable way to flow events up and down through the system. So if the user clicked a button on the web browser, that could be communicated down into the back end. If your data model changed, it could push changes back up to the front end. And they wanted to unify this. They wanted to come up with a single conceptual model for representing this that would enable distributed flowing of events in a way that could be handled uniformly. And the reactive extensions for .NET were what came out of this. And that was what they were originally designed for. They were designed essentially to enable remoteability of event streams. However, this same group then realized that the model they'd come up with was very flexible. It was actually able to express all sorts of interesting computations. And the idea of event streams and subscriptions to event sources were in their own right an interesting entity to have on the back end. And so that same team created a product internally called Reaqtor. So this was only used inside of Microsoft for quite a long time. They did talk about it. So if you've watched if you used to be a fan of Channel 9 back in the day, you have probably come across this before. So Bart de Smet gave a lot of talks about this, and they had hopes to release it. It got used a lot internally. It was behind things like Cortana, and it was used internally in Bing. It's used in bits of Microsoft Exchange. So it got a lot of use, but they never quite managed to get it out of the door. However, fortunately, after some discussions with them about ownership and who was going to maintain it, eventually it did get out there. So that's available, and so we can build on top of it. So the first thing to get to grips with before I talk about what Reactor is like and what sorts of things we can do with it is the underlying model. If you're already familiar with RX, the reactive extensions for .NET, then this will be a revision, but just in case you're not, the basic model presented by RX is really very simple. It's one thing after another. So it's a sequence of things. Those things might be timestamps, they might be measurements of a temperature, they might be atmospheric quality monitoring, they might be key presses, they might be cars driving past a beam in a car park. It could be any event, and they just happen one after another. That's the basic programming model. So conceptually, it's not very different from like an IEnumerable of T. It's just a sequence of things. But the critical feature of RX is that the source decides when to produce an item. So unlike an enumerable of T, where you can just say, give me the next item now, please, give me the next item. You can just write a loop to pull the items out. With observables, the source tells you when it has an item. You know, I as a programmer, can't force the user to click on a button right now. I have to wait till they do it. But when they do it, then that's their choice. So it's in the nature of observable sources that they produce values as they're good and ready. And because the basic conceptual model is just a sequence of things, is the same conceptual model that IEnumerable has, we can use link. One of the things that the reactive extensions and also Reactor give you is a complete set of link operators which you can use to build up queries and to compose computations. And so it's we're able to build on top of this. Sorry, I just noticed there are some chats. Are we still having issues with the audio, or is it okay now? I've just noticed this was from 10 minutes ago.
It's all good. Continue.
It's all good. Okay, right. I will continue. Thank you. Right. So we can build up computations on the link programming model, and this is basically what RX is. And Reactor basically makes that distributed, reliable, and persistent. So at this point, a lot of people say, well, isn't this just like, and they then insert some technology here. So some people say, well, this is just message queuing, isn't it? To which the answer is no, not really. So with message queuing, essentially, message queuing systems are all about the delivery of messages. They provide a safe place to put messages, and then there's a model for consuming them, and they generally give you guarantees like there will be exactly once consumption or at least once consumption of the messages. But they don't generally do any sort of computation over the messages. They don't generally inspect what's in the messages. You can't give a message queue some instructions to say, please group the messages by the value inside this field here, and then give me a sort of a windowed aggregation over the things within each group. You can't do that sort of processing of the contents. It's up to the application code to decide what to do with message queues. So it really isn't like those at all. And it isn't really like event streaming systems either. So things like event hubs in Azure or Kafka, if you're in that world, those often get confused with message queues. They're actually very different concepts. With event streams, the idea is that individual consumers can see every single event in the stream, and there might be multiple consumers. So that's quite a different idea from a message queue where there's generally one consumer per message. So with event streams, again, it tends to be a rule with these systems that they are all about conveying the message, and they have no business with the payload. So generally speaking, if you look at these sorts of streaming systems, they don't know how to make decisions based on what is in the message. There might be some decision making around things like the metadata attached to the message, but nothing that they can actually peek into the messages itself. Whereas Reactor can absolutely do that. Reactor, you generally do describe computations that are going to look in the messages flowing through the system. If you're into this space, you might well go, well, okay, is it like Spark structured streaming then? To which the answer is kind of yes, a bit. You can solve similar application problems with each of these. However, there are some substantial differences with the programming model. The biggest one being that in Reactor, we base everything around expression trees in .NET, and they can be moved around, and it's possible for expressions to be rewritten and distributed automatically outside of query engine processing. So for example, you can build systems based on Reactor where some of the processing is pushed out into edge devices like sensors out in the field, for example. But also the whole thing can be used entirely in process as well. as we'll see, the whole code base for Reactor has been structured in such a way that you don't have to use the processing environment that it provides. You can actually use all the technology it has in isolation or in your own host processes. So, having said what it's not like, what is it like? What sorts of things can we build with Reactor? Well, I'll start with an example that was one of the earlier applications that Reactor has actually been used for in practice. So if you have any sort of digital calendar, most of the ones out there are able to give you notifications to say it's probably time to leave now if you're going to make that meeting. So you have services like if you've got an appointment that requires you to drive to the other side of town and there's a traffic jam, your phone can give you a message saying, you better leave now because it's going to take you 20 minutes longer than you thought it was going to get to that meeting. And so to be able to do this, we have potentially millions of entities in the system, millions of appointments across all the users in, let's say, Outlook.com or whatever, or Microsoft 365. There's loads and loads and loads of appointments all being monitored. Each of them has its own notion of what destination it's interested in. And they all might want to monitor local conditions. So they might want to look at event sources like traffic information. So they might be monitoring the traffic information on certain roads or certain routes. And so they might want to repeatedly update the estimation of how long it's going to take to get somewhere. And so this is very much an event-driven system. So whenever the traffic conditions change, you need to change your estimation of when it's time to leave for an appointment. If someone changes the appointment, that also needs to be updated. And it needs to scale. There are millions of users of Exchange, and they've each got multiple appointments all set up in advance, possibly for years in advance. And these things all need to deliver the right notifications at the right moment. So that's one of the example scenarios. It's lots of events, but also lots of different processing for those events. So the key to understand about this style of thing is we're not just taking a huge amount of data and aggregating it down in a sort of funnel shape. We're not kind of reducing a huge volume of things to a single report. The hugeness kind of flows through the system. You've got millions of people and you've got millions of completely distinct, unique, customized notifications that need to be given out. It's not just an aggregation with a sort of single page result. It's that ability to deal with the scale throughout the whole sort of life cycle of the system is part of what makes these things challenging. So that was one of the things that Reactor has been used for extensively, and it was used to prove out the scale of the thing. It demonstrated that it was definitely able to cope with tens of millions of things happening concurrently. But at Engine, we have used this for some other applications. So one of the systems that we have built on top of this technology was an atmospheric monitoring system. So we ran a project with a local school where we were doing some air quality monitoring with a view to trying to work out whether traffic jams on an adjacent road were causing issues in classroom air quality. And we had, excuse me, these little monitor devices that was bristling with little air sensors so they could measure particulates at various different sizes, CO2 levels, temperature, humidity, and various other chemical sensors and things on them. And they would just report measurements every so often. We had these in a few different classrooms, and we wanted to collect all the data. And these were naturally modeled by the RX abstractions, they're just observable sequences of measurements. But what we also wanted to be able to do was to perform analysis over the stream of events as they were coming in. We wanted to be able to define rules to say, well, if these sorts of thresholds are crossed or if things are changing faster than a certain rate, we would like to be able to respond to that. And so Reactor was a natural fit for that. And another system we've used it for was on a project with a broadband provider. So they have millions of broadband routers in people's homes, and the volume of telemetry that those things are capable of producing is phenomenal. If you looked at every single message that every device in every person's home on a single broadband provider's network was sending at you, it would just be, just an incomprehensibly large number of events. But this company wanted to be able to perform analysis over these things in order to get ahead of problems in the network. So they wanted to find out that things were starting to go wrong before they started getting calls from customers. They wanted to be able to perform a live analysis. They could answer questions like, is this problem happening to just this customer? Or is this a problem affecting all the customers on a particular exchange, for example? Because that's quite an important operational understanding. You don't want to send 30 people out in vans to 30 separate customers when you could have sent one van to one exchange to look at the problem where it's really happening. So this ability to run anomaly detection algorithms, to run moderately complicated computations across very large streams of data, and to be able to analyze things at the level of individual devices, of which there were millions, but also to aggregate and analyze at the level of exchanges, of which there were hundreds. That ability to span those sorts of scales was it was one of the things that made us want to use Reaqtor, and is actually part of what drove us to try and get the thing open sourced in the first place. So those are some example kinds of applications that they might be used for. So with that in mind, let's look in a bit more detail at this so I can get to a point where I can show you a demo. So what does Rx look like? It's pretty simple. You have a type which is actually baked into the .NET runtime libraries themselves called iObservable of T. It's an interface, and it just represents a sequence of things and has a single method, subscribe. The only thing you can do to an observable is subscribe to it. You can say, I am interested in the events that this observable has to offer, so I would like to subscribe to its events. And to do that, you supply a thing called an observer, which must implement the iObserver interface, which requires you to do three things. You must supply an onNext method that will be invoked every time the observable source emits some information. So in the case of our atmospheric monitors, every time we took a reading from a sensor, any observers attached would just get the onNext measurement of whatever it was measuring. There's also an onComplete. Some sources naturally reach an end, and if they do, they call onComplete on their observers. And once they've done that, you'll never hear from them again. Or they might fail. They can say, it's all gone wrong, here's an exception. That should have an exception argument, missing on the slide, sorry. But yes, that will also be the last thing you'll ever hear from a source as well, if it dies on you. So that's the basic model. So now I'm going to show that in the context of an actual application, because people often struggle a bit to see how this could be of any practical value, because it all seems a bit like it might be a little bit Mickey Mouse. So I'm going to show you an example based around shipping data. So there's a system called AIS, which is the Automatic Identification System, which is the system that pretty much all ocean-going boats are required to use. So if they've got GPS transmitters on them, the thing they're actually broadcasting to tell you their location is AIS messages, the Automatic Identification System. At Engine, we supply a couple of free open source libraries. These ones aren't under .NET Foundation thing, they're just free things we provide, called AIS.NET that you can use to process these things. And in this .NET notebook, I'm using .NET Interactive polyglot notebooks to write C# in a notebook. I am going to consume AIS data from Norway. Why Norway? Because the Norwegian government very generously makes a free AIS stream available for all of the ships around Norwegian coastlines. So we have a receiver for that, so we can connect to the Norwegian service to receive all the locations of all the ships anywhere near Norway. You can also run this notebook in a kind of offline mode with a pre-processed data if you prefer not to have it live, but this is going to be live because I'm crazy. We're going to wrap that around a thing that presents it in Rx terms. And then we're going to show all this in a map. I want to be able to show the location of the various ships on a map. So I've got a cell here that just basically displays a map. We're going to zoom in on Norway because that's where the data will be coming from. And scrolling down, I need to hook up my .NET code to the JavaScript that's running the map. And then we are going to arrange to be able to send data from our C# code into that handler on the JavaScript side. This is just a bit of glue so we can connect things together. And then we get to the point of this, which is an Rx query. So this is where we're going to use that receiver host. So the receiver host provides an observable source of messages. So this messages property is an iObservable of IAIS message. And we're going to do a bit of work on it because It turns out that if you want to plot on the map the location and name of a vessel, you can't just read the location and name out of the AIS messages. And there's a reason for that. Ships with GPS transceivers in them send out their location relatively often. They send out messages with their location and speed and heading and a few other things like that, maybe every few minutes, maybe every few seconds, depending on how fast they are moving. They also send out messages that describe the ship's name and its width and its length. They don't send those out very often because ships don't tend to change size as often as they change position, not unless you're having a really bad day in the ocean. So they tend to give us the vessel name type messages much more infrequently. So if we want to show on a map names and locations, we have to somehow reconcile those two things. We have to join them back together. So this is essentially doing a dynamic join over some data streams. So what we're going to do is we are going to group the messages, first of all, by the unique vessel identifier, the MMSI. I can never remember what that stands for, but it's a unique vessel identifier. So this is going to give us an observable source where each thing that comes out of the observable is another observable, a grouped one, grouped by the vessel ID. And then from that stream, we're sort of splitting it out into three different message types. So vessel navigation ones are things like how fast are we going, where are we going, which way are we pointing, and those sorts of things. There's also a separate one for the vessel name and also the vessel type. Is it an oil tanker? Is it a ferry? Is it a jet ski, or whatever it might be? So we get all three of those, and those might all turn up in completely separate radio messages. And then we're going to use RX's combine latest to say, look, I've got three streams here, and I'd like you to combine the latest value from each of those into like a single tuple, and that then becomes the output of our stream. So if I run this, that doesn't start yet. So this is an observable, but it doesn't do anything until someone actually observes it. So we then have to connect that up to all the glue code we had earlier. So this is the point where we're actually going to set up the subscription. And the last thing I have to do is tell the receiver to start receiving, because it isn't actually talking to Norway until I click this button here. So at this point, as long as the demo works, we should be live. So if I scroll back up to the map, hey, it worked. Excellent. So ships are starting to appear on the map around the coast of Norway, and also probably around Svalbard. Yeah, there we go. So all the Norwegian-owned waters, these ships are starting to appear. And as time goes on, we'll see more and more. Because, as I said, they don't all report their name all the time. So we're seeing all the ones where we've had both the name and the location and also the type. So these are color coded in a way. I forget exactly what the colors mean, but you can tell what sort of vessel they are. And over time, they will move around if we sit and stare at them for long enough, and more will appear. So this is an application of RX's ability to do live processing. And I'm just going to talk about it a little more because there's a really important point here when it comes to understanding the value that Reaqtor has to bring on top of RX. So just to recap, our AIS feed, so the raw messages coming out of the ships, you don't get all the information at once. Some of the messages tell you location, some of them tell you the vessel name, some of them tell you other things like the vessel type, some of them tell you the dimensions and so on. But we want all of that combined for any given ship before we can show it on the map. So what we're going to do is group them, as you saw, by vessel, and then use that to combine them. So initially, the first message comes in. And this is the important bit. The group by operator will see that message. It'll use our key lookup and say, okay, the MMSI is 1234 in this case. Have we seen that key before? And the answer in this case is no. So it goes, okay, we need to create a new group. It creates a new observable group for that one. Next message comes in. That's 7977, different one. So it goes, oh, okay, need another group. So we haven't seen that one before either. The next message that comes in, 1234 again, well, that goes out on the same group as the first one. And the next one, also same ID, although a different message type. And at this point, we actually have enough information to report both the name and the location. In the real code, it was actually combining three things, but there isn't enough space on the slide to show that. So we're ignoring the vessel type in this particular example. If you look at the top, the very next message that's going to come in is the name for the second ship. So at that point, that's also got enough to report the combined name and location. And then as subsequent locations come in, it just combines it with the last message of the other type that it's seen as it goes on, and then we're able to process the results. So that's all going on inside the head of that Rx query, if you like. So what does Reactor add to this? Because that demo was entirely based around ordinary Rx using the system.reactive NuGet package. I wasn't using Reactor in that demo, so why on earth was I showing it to you? Well, one of the big things Reactor adds is state handling. So let's talk about state. Some operators build up state as they go. Actually, most interesting operators build up state as they go. So the group by that I used to work out which vessels have we already seen, it's got to remember which vessels it's already seen. It needs to know which ones it's seen before so it can send them out on the group it already created and to know when to create new groups. But simpler operators also often have state. So take, this is one of the operators that's a standard link one, says I'd like to take the first n items from a sequence and then just discard the rest. So if I do observable.take 8, then we get 1, 2, 3, 4, 5, 6, 7, 8 items come in, and then it just stops at that point. So it'll reach the end. So far, so good. But one of the things that Reactor gives us is reliability. So if my server fails, it's able to recover and continue from where it left off. Or even if there's no failure, even if it's just a matter of servicing, even if all that's happening is that my operating system needs an update, or maybe the host software needs to be updated for one reason or another, machines do get rebooted from time to time. And if I set an appointment 3 years ago, I want the reminder to go off, and I don't want to be relying on a machine having stayed up for 3 years just to make that happen. I need the entities in my system to outlive any single process. And that's a problem with classic Rx. If you have an observable with classic Rx and you do observable.take 8 and it starts receiving items, but then you have a reboot and you sort of move into a different process, it kind of goes back to the start. You're going to get 8 items not from the start of the sequence. You're going to get 8 items from whenever you constructed that particular observable. That's not very useful. And this is one of the classic problems with standard Rx, which Reactor aims to solve. It's building in the ability to manage state. All interesting Rx queries tend to accumulate state. If you're doing anything of any value at all with Rx, then in all likelihood, you're going to build up some state that lives inside of the operators in the query that you have defined. And the problem with classic Rx is that this state is ephemeral. It's inside the operators and there's no way of getting it out. So when the process that's hosting these things exits, all that state is lost, like tears in rain. So there's no way of actually freezing the state of some complicated Rx query and serializing it and then reconstituting that later on. And this is one of the things that the Reactor codebase solves. Strictly speaking, it's the reactive bit with a Q. Reactive.link in particular gives you a complete implementation of all of the standard link operators for Rx, but it does them in a way that they're able to manage state. They are able to be interrogated. You can ask them, what state can you write your state out into a store for me? And then later on, you can construct brand new ones, give them back the state store they initially populated, and they will get back into the same state. And so the reactive layer of the Reactor code base provides that implementation of Rx, that state-enabled version of Rx. And then the Reactor layer sits on top of that and provides a checkpointing host. It provides a host environment which knows how to use those state management APIs and can host any number of concurrent subscriptions, and it's able to suspend them all from time to time, collect their state, build a checkpoint, serialize that out to disk or wherever, and then continue. And this is how we're able to build reliable host environments for Rx queries. So I'm quickly going to show you an example of that. So I have running on my computer a local environment that's running a Reactor query engine. And I'm going to create about the simplest query you could possibly create here through this web front end. So I'm going to create this. That is going to hit a breakpoint, which I'm going to move onto the monitor that you can all see. And this is going to use the RX external client API to define a subscription that it wants set up. So it's saying here, okay, I'm going to use the reactive client context. What's that? That's your way in to some Reactor environment. It's a bit like a DB context or in Entity Framework. It's basically your connection to a particular implementation of Reactor. And we're saying to that, I'd like a timer, please. I'd like that timer to wait 10 seconds and then go off every 20 seconds after that. And then I'm using the link select operator to say what I'd like to do with the events that come out of the timer. This timer just produces a sequence of numbers, one after another, on the schedule you specified. And so this says I'd like to take that number and turn it into a string. So this is going to say, give me tick space n. And then it says, well, what am I going to do with that? This is an observable. Actually, it's an iasync reactive observable, but logically speaking, it's an observable. I'll talk about the queue in a minute. And then what do we need to do with an observable? We need to observe it. Nothing. It doesn't do anything until we subscribe an observer to it. So we get hold of an observer. I'm actually using one that's going to put all of its output straight into the diagnostic logging. It's actually going to write events to event tracing for Windows because I didn't want to complicate this demo by having to set up a load of things like event grids and event hubs and so on. So this is just working entirely inside the query engine. And then I'm going to say, okay, I'd like to actually subscribe this observer to this observable. That happens here. And as soon as I do that, that actually sets the thing up and it should be up and running. So if I let this run and then go back in to Visual Studio and look at the diagnostic events, I need to zoom in a bit. Unfortunately, you can't change the font size on this bit of Visual Studio. I am hoping that is legible. Right, so after some point we should see, oh, there it is, tick 0. There's my first tick. So tick 0, after another 20 seconds we should see another one. The thing I wanted to do though was to deliberately kill off the process that hosts this, because the whole point of Reactor is it gives us reliability, durability. I shouldn't be tied to the fact that this query is running in some particular host process. I mean, right now, all these ticks, tick 0, tick 1, tick 2, they're all sitting inside the same process, 70360. If I zoom back out again and go and find my event, my task manager, I should be able to find that. So where are we? Long way down. 70360. That is engine.reactor.sf.query engine host. Okay, so there it is. I'm going to take that out and see what happens. So if I go back to this web browser, if I actually go in, I'm hosting this inside a service fabric for various reasons. If I come in here and find where my query engine host is running. I've got a very simple environment here. Normally you'd have loads of query engines. I've got just one in order to make it really easy to find for the purposes of this demo, because I want to destroy the node that's running on. So it's saying, okay, you're running on node 2 in our compute cluster, so fine. I'm going to blow that away. Let's go into node 2 and say time to go away. If I now, I've got to say, yes, I really mean it. So if I restart that node and then go and look here, I should see fairly soon. There we go, it's gone. I don't know if you can read that, but it's gone. The process that was hosting that tick, 70360, whatever it was, has gone away. But if I come back into here, there's a certain amount of activity has gone on, because it's panicked, it's sort of got a bit, because I rebooted everything. Let's see if that tick was before or after I knocked it out. We're still in 70360 at that point. Okay, so that was before I managed to kill the thing off. But fairly soon, we should see, they're every 20 seconds, I think, I set them up. Fairly soon, we should see another tick coming through. Come on. Oh yeah, everything goes a bit slow when you attach the debugger. Ah, right, yes, this is probably it recovering from a checkpoint. So it would go a bit faster in the real thing. Checkpointing generally happens in less than a second in the real system. I might actually have missed the tick in all of that. Let me have a quick search through it. Oh, tick 8. Ah, different process ID, 1984. So yes, it has managed to move the whole subscription into a completely different process and with no loss of sequence. So the sequence is still counting up exactly as it should be, even though it's managed to move from one process to another. So this is it's a very, very simple subscription. Obviously, I'm just holding tick events from a timer, but the point is that anything that you can set up a subscription for in Reactor, it will migrate the thing from one service to another if something goes down. And that's what enables the durability and the reliability. So to make all of this happen, the Reactor codebase provides various things. So I already mentioned the reactive.link library. This is a re-implementation of RX. So it's basically the most important operators from RX re-implemented with stateful awareness. They're able to write out their current state to a store. They're able to recover themselves from a state that was written into a store, so you can serialize them and then rehydrate them in some different process. We also get the checkpointing query engine, which is the Reactor namespace. That's the thing that actually maintains all the subscriptions and interrogates them and builds up the checkpoint from time to time. So you've actually got an environment that is able to take advantage of those stateful operators. But there are some other pieces as well that enable the distribution of computation. We've got something called Bonsai and we've got something called the Nucleon data model. I'm going to talk about the second one first. The data model enables us to write strongly typed queries against dotnet types that represent the structure of our data streams, but to do so in a way that doesn't depend on those types actually being available on the query engine. Because this is a classic problem whenever you try and remote bits of code around. If you have anything where you're trying to take some code and migrate it from here to there, which is essentially what we're doing. We're saying I'm building a query that's on my client box, but I want that to run inside the query engine. How's that going to work if I don't have all the right DLLs installed on the target system? And in things like Spark, a solution to this is often, well, you just deploy a jar file that has all of the types you need. That's one way of doing it. You just put the code you want into your query engine. But Reactor is designed not to need that, because Reactor is designed to enable you to do ad hoc querying and to change your mind about what the queries are dynamically. And it does this through a system that rewrites the queries to be structurally typed rather than based on any particular .NET type. There's a whole system that enables it to essentially match the shape of the data without really being too fussed about what the actual type is. And this massively simplifies the deployment that's required to work with the types you want to work with. So that's one part of it. But there's another thing called Bonsai that I want to talk about. Bonsai is one of the key enabling features of the Reactor codebase, and it enables expressions to be sent over the network. So you can write a C# expression and Bonsai will turn that into a string of bytes that can be sent over the network, and that string of bytes can then be turned back into an expression later on. I'm going to very quickly show you this. So I have this copy of Visual Studio. Why can I not see that on the web browser? Oh, it's caught up. There we go. Right, so what I'm going to do is I've got a function called show as Bonsai, which does the Bonsai serialization and then just prints it onto the screen so you can see it. And I can pass in an expression. So if I want to see what x plus x looks like, then I can do that. So if I run as far as here, and step over that and then bring the window onto the right screen. That is a Bonsai representation of the expression. If you squint, you can sort of see it. So we've got, it's basically JSON, and this bit here says, here's the expression. It's a lambda. Look at that, that's a lambda arrow. A lambda with 2 arguments. The body of the lambda consists of a plus, and the left-hand side of the plus, the dollar signifies an argument, so it's the argument at position 0. Here's the list of arguments at the end, so that's x. And then the right-hand side of the plus is also an argument at position 0, also x. So that is a lambda evaluating to x plus x. So it's converted this into a string. And if I copy that and stop this and paste that in here, actually it probably is already what it was, and I run a little further and I run this convert Bonsai to expression. So I've completely restarted the process now, so that this is just, I'm feeding a string in. It's just that text that it printed out last time. I'm feeding that in, and it gives me back an expression object, which is a dotnet expression saying x goes to x plus x. So essentially, I've got the ability to serialize dotnet expression trees, to send those over the network. So that's a thing that isn't built into .NET. That's a thing you couldn't do with .NET out of the box, but it's a thing that the Bonsai part of the code base in the Reactor repo gives you. Why is it interesting? Well, it means if you want to write queries that have moderately complicated code in them, that can be turned into an expression tree that can be serialized and then sent over to the query engine. It gives us a way of getting our queries from our client applications that run outside of the Reactor query engine into the query engine. So this whole expression here that says, give me the observable representing traffic information, I'd like to filter it down to just traffic flow data. This is a slightly, but only slightly, simplified version of the thing that does the you have to leave now to make your appointment type notifications. So it's saying, I want to know anytime the traffic flow rate changes, and when it does, I'm going to calculate a new time it's going to take me to get there, and I'm going to set off a timer that's going to go when it's time to leave. So all of this whole thing can be turned into a slightly bigger expression tree and sent into the query engine. So one of the things it enables then is distributed execution, but it also enables other tricks. It enables rewriting of the expression. So because our queries are expressed in a symbolic format now, it's possible for things to actually get rewritten. So most Reactor deployments in practice have a thing called a query coordinator. So when I was talking to the the Reactor system through that reactive client context, I wasn't talking directly to a query engine. I was talking to a query coordinator, and its job is to inspect incoming subscriptions, work out what to do with them, and work out where they're going to run. And as part of that, it might tear them into pieces. It might say, well, okay, you're looking at traffic reports. Actually, we've got a compute node over there that's already doing all the kind of filtering based on routes and so on. So we're going to run that part of your query over there, and then we're going to connect that to this other node that's going to handle the rest of the query for you. Or it might do something like say, oh, okay, that query you've written, that can actually be pushed out all the way to the edge device. So if I've got, for example, one of these air quality monitors, it might work out that the air quality monitor device is perfectly capable of running the filtering that I want it to run. And so it can push that all the way down to the bottom, which might be really useful if you're running in a bandwidth constrained environment, which is often the case if you have sensors dotted all over the place. So this ability to completely restructure the query is made easier by the existence of the fact that these things get turned into a serialized expression. So it means we don't have to have the actual code of the query deployed into the query engine in advance. We can just send it an expression that describes what we want. It can optimize that, it can rewrite it, or it can reject it if it doesn't like it. We don't need to put any code in advance into the query engine. We just send it the expression, and if it's happy to run it, it runs it. Now, one other thing I want to talk about I thought I deleted these slides, but I have to talk about it now because it's on here. So here are some other libraries that do, or systems that do similar sorts of things, broadly speaking to this. I did have a section on how they're different, but I'm running out of time. So the main differences were, well, half of these aren't .NET. So if you want to live in a .NET world, that instantly rules out a load of these. But of the ones that are left, a couple of them, broadly speaking, embrace the actor model, which is a perfectly reasonable thing to do, but it's very different from the RX model. One of the benefits of the RX model is that it's a much more sort of constrained, formalized thing, which enables things like optimization and rewriting and distribution in a way that's much harder to do if your logic is expressed in just plain old compiled C#. But also, one of the big benefits of the way that Reactor library has been structured is it's been designed to enable reuse at a lot of different scales. And the way this works is that there are essentially 3 layers to the libraries. So you've got low level, mid level, and high level. The low level is called Nucleon with a Q. And this is where that Bonsai feature I just described lives. And also it's where a whole load of expression tree rewriting algorithms live, and also a host of other utilities that I don't have time to go into. So all the stuff that was developed that wasn't built into the .NET runtime, which the Reactor team found useful, has ended up in this Nucleon library, and you don't have to be using any of the rest of Reactor to use that stuff. If Bonsai looks useful to you, you can use it in isolation because it's in this low-level library. And then layered on top of this, we have the reactive with a Q libraries. This is where you get the stateful implementation of RX. So it's like regular RX, but with state management. And then the layer on top of that is Reactor, which is where we have the engine that's able to host long-running subscriptions, and it knows how to do checkpointing and how to recover from a failure and all those kinds of things. Now, I've realized I've got to this point and have not explained why these queues keep turning up. So before we stop, I'm just going to explain why everything has a queue in its name. So in .NET framework, .NET runtime as it is now, we have the INumerable interface, which you can run queries over with LINQ, but there's also iQueryable. And the difference between INumerable and iQueryable is that with INumerable, it's all just executable code. If you provide a filter to a where clause, it's just a delegate. It's just a pointer to a function. But with iQueryable, it's all written to accept expression trees. So rather than an actual delegate, what you pass in is an expression tree that describes the filter that you want. And things like Entity Framework can actually take that expression and rewrite it as SQL, and then pass that into a SQL server or whatever to execute the query. So it's doing remote execution of code and distribution in a very similar way conceptually to what RX is doing, to what Reactor is doing. But with Reactor, we actually turn it back into .NET code at the other end as well. So it's sort of .NET at both ends, but it gets transformed on the way. But the queue in iQueryable has been kind of latched onto by all the interfaces in RX that use expression trees rather than just plain old functions. So we have iObservable, is the plain old function-based thing, but there's also iQobservable with a Q, is the version that works on expression trees. So the Q crops up to tell you that you're dealing with a thing that's able to do remoting of expression trees. So that's what the Q signifies. The Q is all about the fact that this works on top of the .NET expression tree model to enable the distribution and rewriting and general optimization of queries across the server farm. Anyway, back to the point about libraries. The fact that it's all carved up in the way that it is means that Reactor can actually run on a wide range of form factors. It was designed on the assumption that you had server farms with about 40 machines in it, hosting hundreds of thousands or millions of queries, but it doesn't have to. It's perfectly happy to run on edge devices. It can easily run on a small Raspberry Pi, for example. It can even be induced to run on much smaller .NET embedded devices like a Meadow. And so you can run smaller bits of the framework, and that enables you to do this pushing out of queries down to the edge. You don't have to run a full Reactor engine on your edge devices. You can just run little bits of the library and it can all work there. So that is one of the big features of this library, is you can use as much or as little of it as you like. So with half a minute to go, Reaqtor gives us event processing with Rx's programming model, but the nucleon and reactive layers of the library may give us stateful and distributed processing of Rx queries, and then the Reaqtor layer on top of that gives us a hosting environment that provides reliability and scalability. Those are the websites for the repos for this and the information about it. I've left you no time at all for questions, but in my defense, we started 5 minutes late. So, do we have any questions? And thank you for listening.
Yes, we do.
Okay.
And actually, it's been answered already. And I see my video is frozen, so that's the best part. So I'm just going to stop my camera. Welcome to technical difficulties. And I'll put it here. Actually, it's more of a comment because Rodney Littles, who we all know and love, he's a great guy. He had a question where he says, so in this level, so is this in some level Rx with wire consistency built in?
With wire consistency, I'm not quite sure what wire consistency means in that, because it's spelled with a capital W. So I'm wondering if that's a reference.
Yeah, capital W.
It could be
to a thing I don't know about.
But then he had a comment, and I'll replace it with that. So Reaqtor knows how much states is being processed. This is amazing. So I think he sort of answered his own question as you were going through the demo, which, by the way, was amazing. I loved it.
Oh, thank you.
It was great. But we don't have a lot of questions. So I think people are afraid to ask questions. Which tends to happen. I do have something here from Johan when he said that Bonsai looks really useful. Thank you for sharing.
Yeah, I think Bonsai is a really critical enabler in this, and just even if that on its own had been released, that would have been really helpful. But yeah, it's a and there's more to say about it, because actually it was designed to work across different languages as well. So internally, Microsoft, I believe, had implementations that use JavaScript as well. But yeah, the version that's been exposed is all .NET stuff. But in principle, it can cross language boundaries as well.
Gotcha. And to add here, this is why I love the internet. This is why I love a live show. Rodney just said, "Yes, amazing. I understood." So obviously, if I want to learn a little bit more about Reactive, I should go to reactive.net and go through. Do you have tutorials? Kind of what does that look like? Can you drive us there quick?
Yeah, sure. So it has. Which window has that opened in? Has it opened in anything? That would be. And oh, there we go. Right. So let me drag that onto the screen. Right. So, and it refused to go on the screen I wanted it to. There we are. So we have API reference documentation in there, and also conceptual documentation. There is also an ebook is available if you don't mind giving us your email address. This is produced by Engine, and it basically tells you all about how Reactor came up. There are various blog posts specifically about Reactor. Also, if you go to the talks page, there are various talks by Bart de Smet, who was one of the principal people behind it, and also a few by me explaining, and by some of my colleagues at Engine, explaining a whole load about all of this. So if you want to get deep into it, then reading those talks will be an excellent place to start.
And I would add also that Engine is a sponsor of the .NET Foundation, so we really appreciate that and all the commitment. And I know I'm talking with Howard about some other stuff that you guys want to contribute more with, which is great. So we may hopefully have more announcements to that here in the coming weeks. And that is it. I've been playing around, see if I can change my camera a bit, and it's not working the way I expected. So Eric, anything to add?
Nothing to add except our sincere thanks, Ian, for that great presentation, including live action demos. I was extremely impressed with the real-time tick events, and I'm sure everybody was.
I was extremely relieved that they worked.
They worked, and they worked well. Thank you. It was fascinating and excellent. And thanks for bearing with us. We started a little late, but you got us back on track, and I thank you very much.
Okay, well, thank you very much for listening to me.
Great.